So this is problem 24 from chapter 28. So 28-24. Here we have a horizontal current carrying wire carrying some current I prime, and on top of this there is a triangular loop, an equilateral triangular loop of distance d from this, and each side of this equilateral triangle is just A, and it is carrying a different current I, and we are required to determine the force on this loop. Okay. So this looks like a straightforward but tedious problem that we simply need to just calculate the force on each segment of this loop because of the magnetic field that's created by this current carrying wire, and then we'll just add those up. Okay? So let's just divide this into a couple parts. So it's 1, 2, 3 segments on this loop, and let's try to determine the direction of the force that these are going to feel. So let's start with the magnetic field. The current is going this way. So in the plane, everything I've drawn here is in the plane of the blackboard. In the plane of the blackboard, the magnetic field is going to be towards us. So I'm going to have some magnetic field pointing towards me. This is not going to be a uniform magnetic field. It gets stronger as I come closer to the wire, but it's going to be all in the same direction, just coming out of the plane, perpendicular to the plane. In particular, because this is in the plane, it's also going to be perpendicular to my triangular loop, simplifying some of the calculations. So the net force is going to be sum of these three forces on the three segments, and F3. And if you look at the direction of these forces, so this is creating a field this way, the current is this way, so the force is going to be downwards. So let's use a different color chalk here. So F3 is going to look this way. And this is of course true for all the segments on that loop, so it's true for their sum as well. Now for this segment, segment 1, the force is going to be this way, the right-hand rule. Again, this is true for each of these segments, so I extend my arm in direction of the current, and I orient my arm such that I can curl my fingers naturally in direction of the magnetic field. The thumb gives then the direction of the force, and by similar argument we are going to find that the second force is going to be this way. Okay? So what we can see here is that these two are going to have their horizontal components get cancelled out, and they are going to end up with a vertical component, whereas it's going to be in the opposite direction to this one. Okay? So if we draw a coordinate system, let's draw one small one here, x and y, we can say that f is purely in the y direction. So this is going to be fy times j hat, and that fy is going to be f1y plus f2y plus f3y. Okay? And that f3 f3y is going to be minus f3. Okay? This f3 is the magnitude of the third force, so that's always positive, but it's in the negative y direction from my choice of coordinate system here, so that's negative f3. These two are going to be equal to each other. Their y component is going to be equal to each other, and if I calculate angle, so I'm looking at this angle over here, it is going to be cosine of that angle times the magnitude of this. So that angle, this is perpendicular, so this is 90 minus that angle, and well, how to do this? So if I draw another vertical, nope, that doesn't work. So, well, this is either 30 or 60, so the way I think about this is that way, it's either 30 or 60. So as I make this triangle longer and longer, as I make this angle larger and larger, this angle also gets larger, so this must be 60. Okay. You can probably show this more rigorously, that this angle is 30, yes, okay. So if I draw this vertical, so these two angles are equal to each other, and the this angle plus that angle is 90 degrees, this angle plus that angle is 90 degrees. So these two angles must be equal to each other. So theta must be equal to 60 degrees indeed. And this one, f1y, is going to be just f1 cosine theta. And this is going to be f2 cosine theta. In fact, these two are equal to each other. So this is going to be twice f1 cosine 60 degrees minus f3 cosine 60 is sine 30, that's a half. So to get is f1 minus f3. Okay? So we need to calculate the magnitude of these two forces and then take their difference. Okay? I mean, there is no deep reason why this final expression looks so simple. It just came out that way in the algebra. Okay? So let's write it this way. This is f1 minus f3 j hat. Okay. So let me now erase this because I will need the room to make the calculation. Okay. Now our task is to calculate this f1 and f3, and it's a little bit easier to calculate f3, so I will start with that one. Now what we're going to do is to utilize this formula. So this is the f is b, I dl cross b, and this b is going to be the magnetic field that's produced by this infinite line of charge, and that b is of course going to be equal to mu naught over 2 pi I over well, some distance. I'm going to call this y. So for b3, this is just going to be the distance d. Okay? Whereas for f1, we are going to need to calculate something that depends actually on our position. Okay. So f3, as I said, is easier to calculate. If I write this down and if I integrate, this is all in the same direction. Everything is just the same. The magnitude of the force is the same. So I can just turn this into a simple length. This is going to be I times A times B3, and B3 using this formula over here, A is going to be mu naught over 2 pi I prime over this y here is d. Okay. So this is mu naught over 2 pi I prime A over d. Okay. All right, now what about F1? Now for F1, we need to calculate the little parts, and each little segment on this side of this triangle, of this loop, is going to feel a different force because their distance from this line of charge, line of current is different, so it's going to feel a different magnetic field. Even though everything else is the same, the magnetic field gets weaker as we move from this point to that point. However, all the forces on this that's felt by every segment on this part of the loop is going to be in the same direction, so I can, in fact, write this. Okay? This is not in general true, but because all of the parts of the force that I'm integrating over are in the same direction, I can turn this vector sum into a simple scalar sum. Okay? And for the df, I'm again going to utilize the same formula. So this is going to be I times dl times just b1. Okay, so this b1 of course depends on our distance, and to do this I'm going to just go from y equals d to y equals a plus d. So that b1 is going to be a function of y, and I'm going to need to express that dl in terms of y in some way. The I is of course a constant. I can take that one out. Right, so how do I do this? So first of all, what happened to this cross product? They're always perpendicular to each other, so the cross product becomes a simple product. That B1 is going to be given by this formula, and as I move from, I can just leave it that way. So let's do it. So I comes up. B is going to be given by this, mu naught over 2 pi this I prime over y, and this dl I need to write somehow in terms of this y coordinate, and let's look at what this dl looks like. Okay, so this is my dl, so this corresponds to a change in dy as well as to a change in dx. Okay? And this angle is going to be 60 degrees for dl. That dl is just parallel to this segment of the equilateral triangle. So I can write that the tangent, the sine of 60 is going to be dy over dl. Okay? So in other words, dl is going to be dy divided by sine 60. Okay? And that is, of course, dy over square root of 3 divided by 2. So this comes to 2 dy divided by square root of 3. Okay? And I can put that in over here. So this is I is taken out. dl is just going to be 2 dy over square root of 3. Okay. Now I can take all of these constants out. I'm going to be left with y in the denominator, and I have these limits of d to a plus d for the integrals. So that integral is going to be a logarithm, and it's going to lead to a difference of logarithms. Difference of logarithms is the logarithm of the ratio. So this is going to be mu naught over 2 pi I prime 2 over square root of 3 logarithm of a plus d divided by d. Okay, the natural logarithm. All right, so this is my f1 and this is my f3. We can simplify these a little bit. This mu naught by 2 pi I prime is a common factor, but it doesn't actually lead to anything very insightful. You just need to take their difference and denote it that way. Okay? So I'm guessing this is just going to actually overcome. It is going to be being pulled to the cable that's exerting a force on it. But you need to go through the calculation to make sure that this is actually the case. Okay. But I'm just going to stop here. But this is the expression you get. That's the expression you get. You get their difference and attach a j hat to the answer. And that's all for this question.